And welcome back. Now, before you get too concerned and thinking, my God, Ralph's lost his marbles here, he's starting to show us a blinking LED, there's more to it than this. This is in fact a very useful pin extender. So when you've run out of pins on your Arduino, and believe me, the Arduino forums are full of people saying, I've got an Arduino Mega, and I've still run out of pins. What do I do? Well, this is the answer. This is a PCF8574T, put that thing in the middle, and it gives you another 8 pins, P0 to P7. Additionally, these can be cascaded because it's run on an I2C bus. And if you don't know what that means, we'll talk about that in a little bit more detail too. But initially, I thought I'd just show you a very, very simple sketch, which as you can see is magically turning these two LEDs on and off. But these two LEDs are not connected directly to the Arduino. They're connected to this chip here, or this little module board I should say, and which in turn is connected by these 4 wires, 2 of which are power and 2 of which are I2C, so SDA, SCL. Okay, so already we've saved ourselves a couple of pins because these don't require pins on the main board. Great. Let's have a look at where I got this from though, because you might be interested in doing this anyway. And there's far, far more to it than just displaying a couple of LEDs, but I thought I'd stop at this point because it's sort of a very useful foundation. So let's have a look at where I got it from. Here we are. So it says here it's a PCF8574 and it's only £1.11. Look, I mean, it's not exactly expensive, is it? £1.11. It took a little while to come from China, although I've said it in a previous video, the stuff from China seems to be coming more quickly these days. I don't know what's going on there, but good if that really is the case, not just my sudden perception of time passing. Anyways, here it is. It's £1.11's worth of stuff. It gives you the chip, a little tiny board, okay, and you see those 3 little toggle switches there. They adjust the address. So if you've got more than one of these, if you've got, I don't know, what does that give you? 3 squared minus 1, 8 possible addresses. I'm not quite sure how that works. I'm not sure if you do get 8 or just 3. It means you can cascade these. So you could have 3 of these, 8 3s, 24 extra pins. And if you're thinking, well, I want to do more than just flash an LED or turn something on, as it were. I want to be able to read stuff in, and how do I know when it's done that? Bear with me, we'll cover all that in this little video. So anyway, that's where I got it from Chip Fans, and it's £1.11, and it's been sitting in my box for a little while, so I thought I'd better get it out and start showing you stuff. Right, let's get to the code window then, which is simplistic itself. It doesn't even use a library, well, other than the I2C library, of course, the wire library. So that's the only one we use because we're controlling all this directly at the moment. Now it might transpire that the use of a library for the PCF8574 might be beneficial, but not at this early stage. It's always useful to understand how this works before we start using libraries. Right, let's go to the code window then and see what we can find. So here we are at the code window, and as you can see we've got the wire library. That's the I2C library, pretty standard, comes with Arduino. I've actually got the debugging window started here, but there's nothing being displayed on it because this is too simple a sketch, would you believe. There's the I2C library. We'll just start it off. This little bit here simply says to this chip here, turn all your pins off. Now stop. That's where we need to do our first little bit of thinking. This is reverse logic to what you're normally perhaps used to on the Arduino, because it sinks current, not sources it, so that off is in fact high and on is low. Why is that? Let me draw you a little diagram. Right, very, very simply then, what happens is this. You've got your plus 5 volt rail up here, your ground down here, and normally you would source from the 5 volts via the nano. So if you had a nano here, or an Arduino, whatever, you have a pin. This provides, if you like, current that way, and it would go via a limiting resistor into your LED to ground. Okay, so you might have, I don't know, 120 ohms there or something. So that provides the current out through the resistor to the LED. Now this chip, the PCF8574, is different. So if I draw that here, so PCF8574, what that's going to do is actually sync the current. So it will come from the 12 volts into your LED and then get sunk by the PCF like that. Okay, now I know you can do this on the Arduino as well, although it's probably more conventional to do it this way, so this supplies current, but the PCF8574 does it the other way, so it sinks current. Which means, of course, that whereas on the Nano you set this high to turn on a digital pin, here high means stop. It puts a barrier up here, doesn't it, effectively? It's basically high potential, which is 5 volts. And when this goes low, effectively what this is doing, of course, internally, is connecting this via the chip down to ground. So low equals on. Here, high equals on. Now, it's very easy to mix these up, or perhaps not to mix them up, but perhaps to forget this, and you start setting bits and bytes high, expecting it to go on, and in fact it does the opposite. So I'm just warning you now, it's probably best to set up a define or something in the sketch to remind you which way around this on. So here we are back in the code window again. So we've explained this a little bit, but we'll just skip over it. If you think, oh, I've no idea what he's going on about here, just accept that this will set all the outputs on here off. Okay, we're setting them all high. Now if you know that a byte consists of 8 bits, and a byte with 8 bits is represented in hexadecimal with F, hexadecimal F, that's what we're doing here. So we're saying set them all off. As I say, skip this if you don't quite get it. We'll expand upon it a little bit later. Here I've done a little diagram to show you what it looks like on this chip here. So the pins at the top, let me just get this a bit bigger. The pins at the top here, look, I've written them out on a little sticky. P0's on the left, P7's 1 from the right. And this rightmost pin is an interrupt pin. We're not dealing with that here, but we most certainly will be using that a little bit later on in the video. Very, very useful, that one. But for the time being, assume that one's not there. We're just looking at P0 to P7. That's your 8 bits output along the top of that header. What we're saying here is then, we're beginning our I2C transmission to this device, and we're saying, that's the device number, by the way, X27, because I've set all these little toggle switches here on. Okay, and I'm going to do a little experiment actually to find out what other addresses I can get out of this. I'll let you know. But in the minute, at the moment it's hex 27, so I'm saying transmit to hexadecimal 27. So that means anything sitting on this I2C bus would receive this request, and they'd all say, that's not me, nothing for me, nothing to hear here, except this one says, oh, hang on, that is me actually. Now, hexadecimal 27 is in fact quite a common value, so the chances are if you're using something like an LCD on here, that might also be 27. So you probably would want to switch these little toggle switches. Okay. Anyway, at the moment, because this is the only one sitting on here, it starts responding. We're saying write this value on the bus to this chip. So we're saying 0B, which means I'm sending you a binary value now, and that means you're addressing each individual bit of the byte coming out, and I'm doing this simply for clarity. So starting at the left, which is P7, working my way down this way to P0 at the end. The only one that's of any use is P0, and I'm saying set it to 0, which, as we've already described via this reverse logic, actually means sync the current. And then end the transmission, then have a little delay, and then we do the reverse. What we're saying is now set P1 low to sync that current, set P0 high again, which is why it's allowing current syncing, setting it off, allowing it, setting it off, and I'm just flipping between the two here just to show you what happens and perhaps make it a tiny bit clearer. Okay, so I'm not going to labour the point on here, but we're talking about bit value addressing. I could have written this as a hexadecimal value because this is going to be 255 minus 1, so 254 would in fact give us that value there, and this one here would be minus 2. Okay, so that'd be 253 would in fact have the same effect, but that's all a bit magic numbery, isn't it? You think, what's that mean? What if I put 238 in there, for example, 0x238? Would you have any clue which bits are set for that? Me neither, not without going to my programmatic calculator, and that's not right, is it? So it's better in some ways, well, better in all ways in fact, to set it as a binary value so you can see the individual bits being set, because that then corresponds directly to this. Well, ignoring the interrupt for the moment. Okay, so that's a very, very simple blink sketch, alternating with this pin extender. So this board here is not connected directly to this one here. It's not using any GPIO pins at all, but we are controlling two LEDs. Okay, so that's the very, very first foundation. And I would certainly recommend, if you're going to get one of these, just to experiment with, or you think, oh yeah, I could use more pins in my project, get this one working first, as it is here. And more to the point, don't just copy what I've done, try and make it work for you. Okay, so instead of using P0 and P1, use P6 and P4 and understand which bits here you need to change to make that happen. Right, I'm going to move on now, and well, two things I'm going to do before I come back to this video. I'm going to find out what hex addresses we can use here, and what else did I say I was going to do? We're going to use a slightly more complicated breadboard. I use the word complicated. If you've seen my videos, you know they're not complicated at all. But we want to know, not only can we set something on or off, how about can we detect switch presses? Yeah, you can actually, which is pretty good, isn't it? And in fact, some can be outputs like this, and some can be inputs. So we'll cover that in the very next bit of the video. Back soon. Right, here we are back again. Now I've changed the circuit board this time, and as you can see, it stopped flashing because we've changed the code, and more to the point, we're now using an interrupt on this last pin here, this thing here. Now, before we go into that, I did say I was going to look at what addresses this could use, and in fact, it is far more than I thought. As we can see here, let me just pull back a bit. So you have literally got the three little dip switches there, right? Those little red things, dip switches. And you can have them as any one of 8 possible permutations. So this can have an address of anything between hex 20 and hex 27, which I've got it running at the moment. That's because I've got the 3 at the top, so on XXX, it gives us hex 27. But if I were to switch 3 down and just leave those 2 at the top, then it gives me hex 26 and so on. So that gives me everything from hex 20 to hex 27. So this gives us 8 pins, and there's 8 possible permutations here. So that means you could buy another 8 of these and connect them up. So you're going to have dozens and dozens of pins, aren't you? And in fact, I saw somewhere that you could get, if you did the configuration right, you get something like 128 pins, although what you do with those. But anyway, there we are. Just goes to show you can have an awful lot of these connected up, all running off the I2C bus, and giving you a lot of permutations. So that's that. Right, now this so this little circuit I've built up here has moved on from the previous one. If I bring up the code window, move back to the top of it, I used the same initial code, but there's a few enhancements. So we went through input outputs. Now input outputs, this was the precursor to the one that's actually running on here now. It was basically the same as the previous one with the toggling of the LEDs, but I had to find out how to set it to read mode and write mode, and that's a little bit, well, convoluted perhaps. Once you understand how it works, you think, oh, so that's how it works. Okay, let me see if I can explain it here. What we're doing in the loop now, so this is the loop where we're setting the LEDs on off. What we're doing now though is saying I want to read the values of those pins. So we have a byte, set it to 0 by default, then say from our hexadecimal address on the I2C, I want to read the value of the pins on here. But it's not just any of the pins. Yes, you do get all 8 bits back, but only those that you've set high are of any use to you. Now if we remember that high basically means off and low means on, it's only the ones that have been set high that will have meaning. So how can I put this? I'm going to draw you a little diagram, and then maybe it'll become clearer. Right, so here we have our PCF8574 chip in the middle, and it's connected of course to the I2C bus, isn't it, along with potentially many other devices. And of course it has its unique address, and that's what enables us to talk to it. That's fine. So there's the I2C bus running past it, and it's just tapping into that. Off it goes into the nether world. Now we're going to have two pins output here. P0, P7, I said output, I meant identified. Let's assume that P0 we want to have as an output, so it's going to drive an LED like you've seen. Now in order to get P0 as an output, we have to specify that the pin arrangement is 0B, so bytes. All the pins are high, in other words off, except P0, the least significant of the bytes. Then it's able to be output. Now P7, we can read in the value on P7 purely by virtue of the fact, look, we've identified P7 as off, it's high, therefore is an input by default. We can say, give me the value of P7. Now we'll give you back the entire byte, but it's still going to work. So that's basically what we're doing then when we're reading from this device. So we can only read things that have been previously set high, that is off, and even then we must put some kind of high value resistor. I think they're suggesting 100k. Can't quite tell what I've got in there now. I think I've got a 10k in there actually, but whatever it is, it sets it high, and then you ground it via your switch. This is emulating here a switch, which I wasn't going to put on here. So when I take this off, that value on here goes low and then back high again. But that's operating via the use of an interrupt, which is not the code we're currently looking at. So we're saying let's read the detail, find out what it is. Now this print binary is something I found on the internet, because what happens of course if you have leading zeros, they don't get printed. So even if you've got an 8-bit binary byte, so 001111 or whatever, the leading zeros don't get printed, and then that's really confusing when you're looking at the output. This little print binary method allows you to print all those bits, and here's the actual code, but it's not my code, it's just something I found on the internet. All we're doing then is saying, well, if that individual bit that I'm interested in is set high, then I want to toggle the LED on and off. The best way to do it is just to do a binary AND. What's a binary AND? Well, we're taking the value, which is, remember, an 8-bit byte, and ANDing it with our fixed value, of which we're only really interested in this one here. The most significant one as it happens. Now this calls for yet another diagram. It's a binary ANDing. We have our 8-bit byte, so we're looking at P7 as the most significant. We were interested in that, and then we're not interested in any others, so we put zeros in for those. So from P0 to P6 it's 0, and we're saying P7, that's what I'm interested in. Is P7 1 or not? So we read in the data, and the data comes in, say, as 0, 0, 1, 1, 0, 1, 0, 1. Some random arbitrary value. What does that mean? Well, when we AND things in binary, it literally means, is this value and this value 1? Well, no, it's not, because they're different, so that's 0. 0, 0 is obviously 0 because they're not 1. So basically all these are 0. 0, 0, 0. And the one we're not interested in any of these results. What we're interested in is this one here. Is position P7 and the data position P7 1? No, it's not. So that means P7 is equal to 0. If, however, the data was not this, if it came in as 1 whatever, we're not really interested in those. We go through all the binary arithmetic for that. We go 1 and 1 is 1. So P7 equals 1 at that point. So we're just ANDing. Is this value, what we've stated, the hard-coded value effectively, and the data we've received 1? But we're not interested in any of these values here because, well, 1 we've set them to 0, so they can never be 1, can they? 0 and 1 is always 0. But this one here, 1 and whatever we've read in that position, is either 0 or 1. And that will tell us whether it's set or not. So back to our code window, we've determined then whether or not P7 is 1 or not, and if it is, we simply call a routine that turns an LED on or turns it off. I mean, it's all very simplistic at that point. It really is LED toggling. Then we have a little delay because otherwise the serial debug window just goes mad with too much data. So that's how we read stuff, and you really need to get your head around this. I'll try and put a bit more description actually into the video blurb, because you do have to understand that to get it to work. You can only read items, bits, that have been previously set high, because otherwise, well, you've already set them to low, which means sync the current, which is basically on. You can't really read bits that you're playing about with. Okay, that's that, and it's all very okay, but it doesn't really help us get much further than I want to know when something's happened on here. I don't want to have to poll this to say, is it set, is it set, is it set? I mean, chances are you might miss something. Doing that is fine for output only. So if you're setting an LED or a switch or a lock or anything like that, that's fine. That can be done in the main loop. But when you're reading stuff in, you want to know about it a bit quicker than that. So how do we do that? Okay, onto the code that's actually running on there at the moment. Very similar to what you just saw, except now, of course, we do have this interrupt routine, and I'm saying if there's a change in the value on pin 2 on my Arduino, then I want to know about it. How does that get changed? Well, basically, the interrupt pin on here, which is the last pin on this little module, the last pin on the Arduino here, on the module here, will go high if there's been a change, but you have to wire up this pin subtly differently. Now let me show you that in the data sheet, because that does explain it rather well. Right, so here we have the Texas Instruments data sheet, and what it's showing you here, look, the interrupt pin, which remember is the farmost pin on there, so pin 8 or the 8th pin, has to be connected to VCC via a 4.7k resistor, and ideally a 10 to 100 PF capacitor to ground as well, which I've also got. And in fact, if we look really closely on here, this is stuck to the thing with blue tack, of course, stop it moving about. Whoops. There you can see my capacitor, and there's a resistor behind it, 4.7k. So the combination of those two at the juncture, just as it shows you on this diagram here, that junction there gets sent to the interrupt pin on here. So when an interrupt is generated by the PCF8574, it brings it low, and the same juncture on that diagram is connected to the interrupt pin on the Arduino, which will toggle the change on there as well. So when this detects a change, it brings it low. So obviously it's high normally, look, through here. Soon as this syncs that and says, oh, there's been a change, an interrupt's happened basically by you touching something over here on one of the other input ports, it brings it low, triggers the interrupt, and the Arduino then also is triggered independently. And you can see that in the code window. Been running it for a little while. So here in the window here, look, it says it's been called. Now you shouldn't really put in serial prints in an interrupt routine, but for the purposes of this we can. So what we're saying is here, look, this ISR change, that's the toggle, that's what gets set by the ISR. So when there is a change, it will change that value, and we do our what LED do I have to set. So the ISR, all it does is say, have I been called in the last quarter of a second? If not, then fine, I'm going to run and set the values accordingly. Oh, Benny's decided to join us. Thank you, Benny. So if we have been called in the last quarter of a second, it'll ignore it. Otherwise it says, right, toggle this flag here so that we can do something in our main loop. Remember, it's a quick in-out on an interrupt. And the fact I've got these serial.prints, that's purely here for, well, initially debugging to make sure it's called, and then so that you can see what's happening. And it's in the main loop, then we say, right, there has been a change, immediately set the flag back to false again so that it can trigger again. We request the status of the pins exactly as before in the previous sketch, and it with our preferred value, so we're only looking at pin 7, print the value in the debugging window and toggle the LED accordingly. So if I go back to the workbench, I'll leave that connected up. So if I take this off now, so basically it's currently connected to ground, but if I take that off, there you can see immediately not only was the ISR called, but the LED here changed from yellow to green. And if I put it back, it goes back. Now you probably might not be able to see it here. Let me clear that. Right, so I've cleared the debug window, so now if I take this off, you'll see it spring into life. ISR called and the value is 1. ISR called and the value is 0. Remember, the value being printed there is from our main loop. So that's how you do the interrupt. So the interrupt on here is called for when any input pin changes. And it's up to you to decide which pin has changed. So if you had, say, half a dozen switches wired up to this, and one of them was pressed, then the interrupt routine would still trigger, but where you're doing this and here, you'd have to say, well, which one of these was in fact pressed? Am I interested in this one or this one or this one, or whichever one it is, and you work your way down until you find out which one was pressed. And in fact, you might even be able to do multiple ones there. I'm not sure about that, so don't quote me on there. Right, basically that's about it. What I'm going to do is give you 3 sketches then. One's the ridiculously simple blinking LED, but it actually does show that this works. The second one is where you read the data, so it's effectively this code without the interrupt routine. And then finally the third sketch is more or less the same code as this, with an interrupt routine, and I might just put a few more comments in, and I'll put the URL of where I got that print binary from as well. It was just easier than trying to write it itself. I thought that serial.print actually in the Arduino would take care of that, but apparently not. Even if you set it to bin, you know that, for example, you can do serial.print, open brackets, value, comma, bin, close brackets, and that'll print the binary equivalent of the integer value you're putting in there, but it still doesn't print those leading zeros. Not very good, is it? Because then you can't really tell what value it is. Okay, right, that's it. Very simple this. Only £1 or just over £1, wasn't it, from China? So if you're running short of ports, this is definitely the way to go. It's simple, cheap, and once you've got your head around that input-output bit, easy as pie.
That was easy.
That's it. See you in the next video. Thanks for watching. I hope you're finding these videos useful and interesting. Please leave comments down below, subscribe, share, and give me a thumbs up. Thanks for watching. See you in the next video.